Hello, we're here today to introduce to you Inkogether, which is a real-time collaborative drawing and guessing game built as a final project for a distributed system course. So first, we're going to start with the problem statement and our motivation to build this application. We built Inkogether because we wanted a drawing game that felt more engaging than the ones we already knew. Here are some of the existing games on the market right now. We have crdt. One player draws, the other watch and type, but there's no real teamwork. You are not drawing together on the same board at all. Next up, we have scribble.io. If you guess automobile instead of car, even though they mean the same thing, but you still get 0 point for that. Next, we have aggie.io. Here, we have the collaborative canvas, but there's no guessing element, no competitive. Then we have Jackbox. Still one player, one board, no collaborative. And that is why we should inkogether, because here we have all of that. Zero install, join by code from browser. Team collaboratively draw together on the same board. AI scoring so you don't get penalized for saying automobile instead of car. AI generative drawing prompts for every new single game. crdt based canvas for real-time synchronization. And everything is open source. So if you are newly met strangers, you're looking for an icebreaker game, you don't want any single player spotlight awkwardness, or groups of people who actually want to play and draw together, and so many more. Inkogether is the one for you at no cost. Now it's time for the demonstration.
Thôi kéo. Rồi, vô bài mọi người. Vô trên room nè. 6. Ai muốn nuôi đi. Đúng tiền. Mày biết quá. Quên rồi. Is that good? Okay. Open again.
Now we moved on to part 3, system architecture. First, we start with the system use cases. You can probably tell from the demo there are players, and for each room, there's also one host. So players have these actions, join, chat, toggle, so on and so forth. Host is also a player, but host has additional actions, such as create room, start game, replay and end room, while regular players do not have these. We also have Gemini API as an external actor, only called to generate AI prompt or score the guesses. Now we move on to the overview of the architecture of the system. Here we have 3 tiers. The first one is the client tier, which is a React single-page application built with Vite, and it communicates over WebSocket via Socket.io for real-time events and over HTTP for room assignment queries. Application tier. 3 Node.js servers from app 1 to app 3, each running Express and Socket.io to hold connections with its clients. So in this architecture, servers never communicate with each other directly. Between client and server, we have a load balancer. Its job is to route connection of a client to a specific server. Client A could be routed to server app 1, or that client A could be served by server app 2. It depends on the load balancer. Then we have the coordination tier, which is a single Redis instance used exclusively as a key value store. So an entry in Redis would be like room BCD mapped to server 3. Redis is never used for event delivery. Then again, we have Google Gemini, called only by the scoring pipeline and not involved in the stroke delivery or phase transitions. So let's get into the WebSocket to understand how client and server communicate. So client opens the inkogether URL, gets its own socket ID served by server K. Now a client A creates a room ABCD and then joins it. So the socket of client A will be subscribing to all the events in that room ABCD. Then we have client B also joining that same room ABCD. The socket object of client B will also be subscribing to that room ABCD. So when the room ABCD moves to a new state or a game event happens, then server K will be broadcasting that events to all the listeners of the room, which are player A and B. For example, server K will broadcast the game has moved to the draw state, or a player with this user ID has left the room. So all the clients in the same room listening to this room events will be updated with the newest event. But our system is a distributed system, and we do not just have one server K. Instead, we have a load balancer and multiple servers behind the scenes. So now, for example, we have player C also wants to join that room ABCD, but the load balancer is not capable of understanding that. It blindly routes player C to a different server M, but server M has no knowledge of room ABCD. Only server K has that. So player C, being on a different server, cannot listen to the event of a room ABCD on server K. Basically, player C is now isolated. That leads us to the core distributed challenge. When a load balancer distributes player, two teammates can land on different servers and start receiving each other's events. So there are some approaches to solve this problem. The option 1, we will have a shared database per event. Option 2, we will broadcast all the events via Redis, pub, and sub. Option 3, ownership routing, which is the one that we did. We make sure that every players of the same room will be routed to the same server. But before we got to approach 3, we will walk you through all the previous ones to show you why we didn't choose them and why we ended up with approach 3. Approach 0 would be a single server in the middle, where all the clients will be connecting to that single server. So the good point is, it is simple when we try to broadcast events to all clients. But the problem here is, this is a single point of failure. This server dies, all the games are gone. It cannot be scaled horizontally, and it has a port limits problem. So we did not choose approach 0. Approach 1, shared database. So we have multiple servers and a shared database. Now, on each server, we do not store any room state anymore, but instead, we move the room state into a shared database so that any server can handle any player. This removes the single point of failure, but each read and write operation every second per user adds latency to every stroke, and the database quickly becomes the bottleneck. Approach 2, Redis pub sub adapter. We keep the room state in the server's memory now, since we do not have any database anymore, and we use a Redis message broker to forward only the new changes between servers. So server A publish room A stroke to Redis channel. This will be broadcasted to all the servers subscribing to this channel. But the problem is maybe server 2 is not even serving any user right now, or server 3 does not serve any player in room A. So both servers do not need that room A event. So we didn't choose this because it wastes CPU and bandwidth processing irrelevant events. Approach 3, the one that we chose and actually implemented, is ownership routing. We guarantee that every player of the same room is on the same server. So now for each room, Redis only hold one entry. For example, for room 1, it maps to app K, or room 2 to app M, and so on. So how does this work? Let's take a look at our room join sequence. Client A creates a room ABCD on server K. Server K will write to Redis that room ABCD is at app K. So we come back to our problem. Client C wants to get to the room ABCD on server K, but the load balancer is not that smart. It routes randomly player C to server M. So let's visualize that. When player C joins room ABCDE, they have a GET request at this API endpoint to that room ABCD, so any replica can answer this. In this case, it is our server M answering this. Then server M will query Redis to ask where room ABCDE is currently at. Redis answers it is currently at app K, so the server will return app K URL to the client. Client disconnects from random replica, which is server M, and reconnects to the owning replica, server K. Client can now join the room event and listen to the full room state. Next up, part 4, crdt canvas synchronization. One of the significant problems is the synchronization challenge. Player A draws a stroke, and player B erases that same stroke at the exact same millisecond. How to decide which operation goes first, or how to make sure that A and B both have the same board state. So our approach is CMRDT, operation-based grow-only set with Lamport clock synchronization. That seems like a mouthful, but I will break it down to you, all these little terms. CRDT is a special data structures for distributed systems. Its superpower is strong eventual consistency. In a standard system, Alice draws, the central server will lock Bob's. And then when Bob draws, the central server will block Alice's operation to decide who were first. With CRDTs, there's no central server making that decision. For example, we currently have a board with a dot. Clients can make changes locally without waiting for the server. Alice makes her changes, it updates locally immediately on Alice's screen, so Alice does not feel the delay. Same for Bob and Carl. Then no changes get forwarded to the other clients of the same room. CRDT's mathematical rules guarantee that if two clients have received the same set of updates, their final state will be exactly identical, even if the arrival order is different. So Alice, Bob, and Carl board all arrive at the same state. So we know the purpose of CRDT. You probably also noticed that there's a word operation based. As you saw, Alice only sent the specific operation, which is letter A, she just performed, to Bob and Carl instead of her full canvas history. So that is operation based. And operation based saves a lot of bandwidth. You already knew operation-based CRDT, now we add a new term, grow-only set. For operation draw, currently our set is a dot. Alice, Bob, and Carl draw and exchange new changes. So our current set of stroke grow larger. It adds more to the set. So when we draw, the set only increases in size, never reduces. And what about operation erase? So now this is our set because of how the whiteboard works, so you never actually delete data. So if Carl draws a line and Alice erases it, Alice isn't deleting Carl's line from the database. Alice is adding a new eraser stroke on top of it. Therefore, data structure only ever grows. Now how can we know which strokes should go first in which order? Should it be .abc or .bca or .acb? We will need the help of a third factor called Lamport clock. This is the current set that each player holds. With each stroke, we also attach with it a clock value. So at the end, each player can reorder their own set by themselves and all arrive at the same consistent order, therefore the same board state. Note that we don't use real timestamps in distributed system because Alice's computer clock may be 2 seconds faster than Bob's. So instead we use a Lamport clock, which is an integer counter on each client. So let's walk through how it works. We have client A and client B. They both have their own separate Lamport clock. Clock A of client A is at 0 and clock B of client B is at 0. So client A draws red stroke. Before they act, increase the local clock by 1. Insert the current clock value stroke into the local key set, renders immediately on client A screen before sending the delta to the server. The same happens for client B. Draw a stroke, then increase the clock, add to key set, renders, and send. Server receives both deltas, forwards each to all teammates. No order is imposed by the server, and the arrival order does not matter. Client A receives B's delta, update the local clock of client A to the maximum of her current clock and the incoming clock value. Insert B's clock to the G set and sort. But notice how the time is both 1. How can we sort? We introduce a tiebreaker with their client ID. In this case, A comes before B, then client A wins. On the client B side, the process is the same. It doesn't matter who's right, it only matters that both computers resolve the tie the exact same way, so they are both identical. So using this method, both clients arrive with the same sorted, consistent order of strokes. This merge algorithm is safe because it satisfies all the properties of a CRDT. Commutative, arrival order does not matter. Associative, grouping does not matter. Idempotent, duplication does not matter. Move on to how we integrate AI into our system. For drawing prompts generation, we use Gemini 2.0 Flashlight to generate 2 independent prompts, one per team at the start of draw phase. So the prompts are generated server-side and broadcast with the game phase events. Prompt has the format of subject, action, object. For example, a robot eating spaghetti or a cat riding a bicycle. On to the scoring pipeline. We have the function to compare the guess and target, which runs through 3 sequential stages. Stage 1, exact match. Both strings are lowercase and trimmed. A match returns 1.0 immediately. Stage 2, local heuristic. 2 metrics are combined as a weighted sum. We have the word overlap. F1 measures how many content words the strings share. Then the bigram check card measures character level overlap, handling slight misspelling. And if the computed Q is smaller than 0.5, then we call Gemini 2.0 Flashlight, requesting a JSON score between 0 and 1. The call is raised again a 3-second timeout. On the timeout or failure, we fall back to the queue. Part 6. Evaluation and results. We tested 50 guest prompt pairs. 14% resolves in stage 1, 48% needs to move to stage 2 to resolve, and about 38% needs to make an API call. So overall, 62% resolve without an API call. About the mean latency per scoring stage, we have extremely low latency for local stages. To summarize, exact matches resolve under 1 millisecond. Local heuristic resolves around 12 milliseconds. The remaining 38 went to Gemini at a mean of 480 milliseconds. Overall, 62% of guesses were scored locally under 30 milliseconds. We tested this with 4 clients, 2 per team, spread across different servers. Join flows were verified with client initially routed to the wrong server. Redis cleanup, entries delete immediately on normal end and on all player disconnect. If the host left, another player get promoted to be the host to continue the game. For the draw phase, clients no longer depend on the network arrival order. To conclude, our system works well, but there are a few areas for future improvement. We currently rely on in-memory state, static replica discovery, and a growing crdt dataset. While production deployment would also require stronger validation, course controls, and timing optimization. The key takeaways are: first, smart routing simplifies synchronization. Second, CRDTs enable real-time collaborative drawing without central coordination. Third, our tier AI scoring resolved most guesses locally. Finally, this project provided practical experience with real distributed system challenges.
Thank you for listening. Hit that subscribe button.